Okay, today we're going to get into section 2 of the chapter on applications of gravity. But first I want to finish up where we left off yesterday because the timer almost ran out on me. So this is the very end of section 1 where they show this graph. The x-axis, you have the distance from the gravity source, the planet or whatever, to wherever the object is. And here is the magnitude of the gravity force. Notice when you're small distance from the object, you get a large gravity force. As you move away, the gravity force decreases quite rapidly and then levels off. That's actually just a y equals 1 over x squared graph. So that's how we get the whole inverse square thing. Well, that's what the result of the inverse square thing, I should say. Now, notice a couple things. First of all, as you get closer and closer to the object, the gravity force is going to rise up toward infinity at a distance of 0 from the object. That's assuming you're talking a point mass like a black hole. And that is true. You get this really steep gravity shear as you get closer and closer to it. That's why they kill you. When you're this close, the gravity force at your feet and at your head are very different values, and you get stretched out, or spaghettified is the technical term for it. On the Earth, well, I guess if you got infinitely close to a point mass, the mass of the Earth, the same thing would happen. But the Earth itself has a size. Its radius, the surface of the Earth, might be right here. So here you are, you can't get any closer than that because it's not a point mass. And so you'll never have to worry about being spaghettified by the Earth. As you move away from the surface of the Earth, the gravity force drops off until you're out here in space. Notice the further you get then, it drops off towards 0 asymptotically. So at an infinite distance from the Earth, the gravity force will be 0. But anything beyond that, you have some gravity force. However, if you're bazillions of kilometers away, the gravity force is going to be so small it might as well be 0. Until you get close enough that it starts rising up and turning the corner here. So that's that. That graph will come back into play when we talk about gravitational potential energy. Now, something else they mention here is that gravity is a force and works like any other force. So if you have two gravitational forces, they act like vectors. Or if you have gravity force plus some other force. You've already been doing this whenever you put in the mg force in a free body diagram. You're treating a gravity force and using it like a vector and doing vector addition or whatever else you did. If you had two gravitational forces, say you're floating somewhere between the Earth and the Moon, you would treat them just like any other force vectors. The gravity force vector of the Earth is pulling you toward Earth. The gravity force vector of the Moon is pulling you toward the Moon. If they're exactly opposite direction, like you're legitimately between the two bodies, then they subtract from each other. If they're at angles to each other, because you're off, at an angle between the Earth and the Moon, then you have to add them like you would normally vectors, like parallelogram method or whatever. So that's that. Now, this concept of force field, Newton came up with this idea to kind of explain what gravity is, although it's not much of an explanation. A field is simply a region of space with a collection of force vectors. So the Earth is surrounded by force vectors. If I take a representative mass of exactly 1 kilogram and move it around from here to there to there to wherever, I can map the force vector on that object, the gravitational force vector on that object. And then I take all the infinite number of force vectors for all the infinite positions, put them together, and that's the gravitational field or the force field around the Earth. Notice the field vectors for gravity always point toward the center, and their magnitude decreases with distance squared. So here, the gravity force is fairly large. Out here, the gravity force, same direction, but rather small. Okay, so a force field is just a collection of all the force vectors surrounding a body. The same would be true of an electric field or a magnetic field surrounding an electric source or magnetic force. Now, applications of this. Newton, you have to use calculus to do this. You have to use integration to do it. I'm not sure if you guys got there yet or not. You hadn't last time we talked. If you use integrations, you can prove that for a spherical object, it behaves just like a point mass, as long as you're outside the sphere. Not, you can't be inside the Earth, it won't work then. But as long as you're outside a spherical Earth, the gravitational force works as though it were a point mass, which makes life nice and easy for us. We don't have to account for the size of the planet. Well, we do have to account for the size, but we don't have to account for the shape of it or whatever else. We can just use point mass. So that's that. Now, this we already talked about. That's the Newton's law equation, if you forgot it. Hopefully you didn't. And then here they're showing, treated as though it were a single point rather than a giant sphere. Notice when we talk about like the planets orbiting the sun, they're so far apart that the size doesn't even matter, and we do treat them directly as point masses. When you're dealing with an object on the surface of the Earth, like here close to the Earth, you can still treat the Earth as a point mass. The gravity force will still apply, but you got to be careful. If I tell you how far above the surface the object is, you have to add the radius of the Earth in there to get the radius from the point mass, not the radius from the surface. Now, using this equation, the Newton's law force equation, we can actually do some fairly straightforward calculations and find the value of g and find the mass of the Earth. So let's start off with, well, let me slide back here. The force of gravity of an object, say you standing on the surface of the Earth, is equal to the constant, that 6.67 times 10 to the minus 11th, times your mass times the mass of the Earth divided by the distance squared between you and the center of the Earth, because it's acting as a point mass. Well, the distance between you and the center of the Earth is just the radius of the Earth. So we can plug that in there. We can plug the mass of the Earth in there. We can plug your mass in here. And that's the constant. You can plug that in. We can find the force of gravity acting on you. That force of gravity acting on you, remember, is just your weight. So we can, instead of writing F there, we can write mg, because that's what your weight really is, and then simplify. Notice it's lowercase m. It's your mass times g, not the Earth's mass times g. So mg equals this Newton's law nonsense. Notice your mass cancels out. Doesn't matter what your mass is. And we get g, 9.81, equals the capital G constant times mass of the Earth over radius of Earth squared. Which, notice the PowerPoint, which the book made, is wrong. That m shouldn't be there, right? It should be lowercase g equals g times, cross that out, mass of the Earth divided by radius of the Earth squared. So, bottom line is, the gravity on the surface of Earth, that 9.81 we've been using since we've been born, is simply equal to the universal constant times the mass of the Earth over the radius of the Earth squared. If you look up the mass of the Earth and the radius of the Earth, plug them in, you can actually solve for gravity on the surface of the planet. And when you do so, you get the 9.81 meter per second squared that we've been using all along. So, yay, Newton's law works. Even better, if we want to go to the moon, we can plug in the mass of the moon and the radius of the moon and find out gravity on the surface of the moon, what it's like there. And we get not 9.81 because the moon has a different mass and radius. Same for Mars or any other planet. I think they show that. Oh, okay. Before they show that, they show this fun little gravity map. Because the Earth is not perfectly spherical, and also because there's it's not uniform in distribution as well. There's regions of ores and whatnot that increase or decrease the local mass distribution. Gravity is not exactly 9.81 everywhere. It's a little higher, a little lower, whatever. Notice here we are in this fairly low gravity region. You feel how low gravity we are here? We're almost floating, aren't we? Instead of 9.81, we might be at 9.806 or some such. Look over here in Japan, they're in a very, very high gravity area. That's why they have all those kaiju like Godzilla from the high gravity, and why they have to all go around wearing mechs. Okay, so anyway, back to the equation. the surface gravity of any planet is equal to the constant times the mass of the planet over the radius squared of that planet. So again, plug in mass of Mars, radius of Mars, you can find what the gravity on Mars is like from when you take the field trip there. Oh wait, field trips are canceled. Coronavirus on Mars, we can't have that. So here they do an example with the moon. They give us the mass of the moon, they give us the radius of the moon. So plug in capital G, mass of the moon, radius of the moon squared, do all the math, crunch the numbers, and we get 1.62 meters per second squared, which is the surface gravity on the moon. By the way, you can divide that by 9.81, find out it's about 1/6 of a G. So if you go to the moon, you would weigh 1/6 of what you weigh on Earth. Now, last thing to talk about today, and I got like 4 minutes to do this, is good old Cavendish. He finally, in Newton's day, they couldn't figure out what capital G was. They knew the equation, they knew it had to be true, but they couldn't get the actual numeric value. Because it's a tiny number, it's hard to measure. So here's how Cavendish measured it. He took two massive lead or whatever spheres, and then had two tinier lead spheres suspended from a thread. And now bringing them near the more massive spheres, gravity force will provide a very, very tiny force on this mass and on this mass, putting a torsion force on that thread and making it twist a little bit. Now, putting a mirror there and shining light and reflecting it, as that mirror twists, the angle of the light beam twists by double the amount. It kind of amplifies the amount of twisting and allowed him to measure on a scale how much twisting and therefore how much force there was. By measuring the force, he could plug into Gm1 over m2 over r squared and calculate what G must have been. And so he found capital G. They often say he weighed the Earth because they didn't know the mass of the Earth back then. But if you now know the value of capital G, you could plug all this in knowing 9.81 and calculate the mass of the Earth, kind of backwards what we did on the previous slide. And so once Cavendish measured the value of the constant, capital G, they could plug in and actually find the value of the mass of the Earth. So they say he weighed the Earth, he actually calculated the mass of the Earth given the constant that he could measure. So that's that. Whatever they do, another example, you can work through that on your own if you like, to get the mass of the Earth. And this isn't terribly important here, and I'm running low on time. Given that they know the mass of the Earth, they could then use the radius to calculate the density of the Earth. And notice the density of the Earth is much larger than the density of rocks that we see at the surface, which gave them their first big clue that the core of the Earth is more dense than the surface. And so starting to figure out the interior structure of the Earth came from that. Last thing they talk about here is with formation of black holes and whatnot. I'm going to save that for later because after we get into gravitational potential energy and things like that, which the book doesn't cover, but we're going to, I'll give you a better equation for calculating how you get black holes. And the same thing with this last slide on general relativity. When we go into relativity, which maybe next chapter, maybe I'll rearrange depending on when we come back to school, we'll do an entire chapter on relativity, and then we'll get into details of this later. And that brings us back to circular motion, which we already did, so we're done with this. To make sure you know what you're doing here, I'm going to give you some more book work to do. I know you hate the book work, but we'll do some more book work on this, and then maybe tomorrow we'll recap with a worksheet of my own that I do, and combining the last couple of lectures together. Make sure you got it. All right, until then, enjoy physics.